Hello and welcome back. In the previous video, we were discussing conservation of momentum, and in this video, I stated that the momentum immediately before a collision will equal the momentum immediately after a collision. In this video, I want to build on that and talk about the different types of collisions that can occur. And then I'm going to work through a couple of examples. So it turns out that all collisions can be broken up into one of three types. There are elastic collisions, and these are collisions in which both energy and momentum are conserved. Then there are inelastic collisions. These are collisions in which momentum is conserved, but energy is not. Finally, there are perfectly inelastic collisions, and these are actually a subset of the inelastic collisions. These are collisions in which the objects stick together after colliding, and in this case, momentum will be conserved, but energy, again, will not. Now, elastic collisions may seem like an idealization. It may seem like something that never actually occurs in real life. However, elastic collisions occur very often when objects collide without touching. Now, what exactly do I mean by that? Well, I have two examples here to kind of illustrate this point. One example is what's called a gravitational slingshot. So this is when a rocket travels very close to a planet and comes in moving one direction and then moving out in the opposite direction. So this is a very good example of an elastic collision because no energy is lost. Another example of an elastic collision occurs when you have two electrons moving towards each other. The electrons will repel each other and move in opposite directions. So this is another example of a very good elastic collision. Another example of an elastic collision, or very nearly elastic collision, is the collision between very hard objects, such as a collision between billiard balls. Inelastic collisions are far more common. So an example of an inelastic collision is a collision between two cars. Now the reason that energy is not conserved is because some of the kinetic energy of the cars winds up getting absorbed by the cars when they collide. So when two cars collide, the bumper and the car deform. When this happens, the atoms inside the metal of the car, the bonds between them wind up stretching and increasing the potential energy between the bonds of the atoms. So what happens is that some of the kinetic energy of the cars winds up getting converted into potential energy between the atoms inside the metal. Now, a perfectly inelastic collision, remember this is a collision between two objects that stick together. So examples of this is like when a meteor hits the Earth, the meteor gets embedded inside the Earth. Other examples, a very, very common example that's used in physics classes, is when a bullet or an arrow hits a target and then gets stuck inside the target. So here I just have an overview of the different types of collisions. So during an elastic collision, there are four different variables we have describing the velocities. There are the two initial velocities and then two final velocities. So we have two different final velocities during an elastic collision. However, we have two equations that we can use to describe elastic collisions. We have conservation of momentum, and we also have conservation of energy. Now, perfectly inelastic collisions will be really the only types of collisions that we'll study in this class. And during these collisions, there will be two initial velocity, but only one final velocity. There's only one final velocity because the two masses will stick together, so they'll be traveling with the same final velocity. And during these, we only have one equation, and that is conservation of momentum. So let's go ahead and look at an example. This example says a 0.2 kilogram bullet is fired at a target which has a mass of 2.5 kilograms. The bullet gets stuck inside the target, so this means it's a perfectly inelastic collision. What is the ratio of the final to the initial kinetic energies? So we know that during perfectly inelastic collisions, the kinetic energy won't be conserved. However, during any type of collision, we always have that momentum is conserved. So we know that the initial momentum is equal to the final momentum. Now, initially, before the collision, the only thing that's moving is the bullet. So the initial momentum is equal to the mass of the bullet times the initial velocity. And after the collision, the bullet is embedded inside the target. So these two things, the mass and the target, will be moving together with the same final velocity. So the final momentum is going to be equal to the total mass of those two things, it's the mass of the bullet plus the mass of the target, times the final velocity. So if we set these two things equal to each other, so if I set this equal to the mass of the bullet times the initial velocity, I can see that the final velocity is going to be equal to the mass of the bullet divided by the sum of the mass of the bullet and the mass of the target times the initial velocity. So now all I need to do is plug that back into the equation for the kinetic energies. So we're looking at the ratio of the final kinetic energy divided by the initial kinetic energy. And remember, the formula for kinetic energy is 1/2 mv squared. So the final kinetic energy, this is 1/2 mv final squared. And the initial kinetic energy is 1/2 mv initial squared. And actually, we need to be a little bit careful about this. Let me erase this. Initially, the only thing that's moving is the bullet. So the mass we have is the mass of the bullet. And in the final scenario, the bullet is attached to the target. So the mass of the whole thing is the mass of the bullet plus the mass of the target. So now if I plug in my equation that I found on the previous slide for the final velocity, so we have 1/2 times the mass of the bullet plus the mass of the target times, and remember this is the mass of the bullet divided by the sum of the two masses times the initial velocity squared. So we have the mass of the bullet divided by the mass of the bullet plus the mass of the target times the initial velocity, and that whole thing is going to be squared. And again, we're still dividing this by 1/2 times the mass of the bullet times the initial velocity squared. So right away we can see the 1/2s are going to cancel. And now what I want to do is I want to go ahead and actually distribute this square to everything inside there, and we'll see what else cancels out. So we have the mass of the bullet plus the mass of the target. And now this thing, so I'm going to distribute the square. So we have in the numerator here, we have the mass of the bullet squared. And in the denominator, we have the mass of the bullet plus the mass of the target, that whole thing squared. And then we have the V0 also being squared. And all of this is divided by the mass of the bullet times V0 squared. So looking at this, up in here in the numerator, we have the mass of the bullet plus the mass of the target in the numerator here, and then two of them in the denominator here. So this is going to cancel with one of these two, so we'll get rid of that square. The mass of the bullet in the numerator here, and the mass of the bullet here, those will cancel. So it cancels with one of these two. And the initial velocity squared will cancel. So what we see is that this is just going to be equal to, so we have one of these left, so we have the mass of the bullet in the numerator, and in the denominator we have the mass of the bullet plus the mass of the target. So it turns out that the ratio of the final kinetic energy to the ratio of the initial kinetic energy is just equal to the mass of the bullet divided by the total mass of the bullet and the target. And this is equal to 0.074. So only 7.4% of the initial kinetic energy is left after the bullet gets embedded inside the target. So now in this next example, what I'd like to do is I'm going to work through a perfectly elastic collision. So this is a collision in which both energy and momentum are conserved. And I want to look at just the most general case. Well, not really the most general case. I want to look at a case in which one of the masses is initially at rest. So we're going to have two masses, m1 and m2. And m1 is going to be moving with an initial velocity v0. And so m1 is going to collide with m2, and then after the collision, the two masses will be moving like this in opposite directions. And I'm going to solve for these two final velocities. So we have the final velocity of mass 1 and the final velocity of mass 2. And I'll solve for these two unknowns using conservation of energy and conservation of momentum. So in this example, we have mass 1. It is initially moving with the velocity v0. And I'm just going to call this initial velocity v0 because mass 1 will be the only mass that is initially moving. Then after the collision, I'm going to call the final velocity of mass 1 v final 1 and the final velocity of mass 2 v final 2. So because this collision is an elastic collision, we have both conservation of momentum and conservation of energy. So we have two equations and we'll have two unknowns. So we need to start out by solving one of the equations for one of the unknowns in terms of the others. So I'm going to start out by looking at conservation of momentum. So we have that initially, we have that the initial momentum is going to be equal to the sum of the final momentums. In the initial momentum, right, initially, all we have is mass 1 moving with the speed v0. So the initial momentum is just m1 v0. And then the final momentum, we have both of these two masses moving, so it's going to be m1 times v1 final plus m2 times v2 final. And so what I'm going to do is I'm going to solve for m1 v1 final in terms of these other things. So I'll have m1 v1 final is equal to m1 v initial minus m2 v2 final. And at this point, I'm just going to leave that equation as it is. I'm not going to try to simplify it any further. Now I want to look at conservation of energy. So conservation of energy tells us that the initial energy is equal to final energy. And in this case, the only real energy we have is the kinetic energies initially of mass 1, and then the kinetic energies of mass 1 and m2. So the initial kinetic energy is the kinetic energy of mass 1, so this is 1/2 m1 v initial squared. And the final kinetic energy, this is 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. And so what I'm going to do, well, right away what I can do is I can get rid of these halves. And now what I want to do is I want to take this whole equation and I want to multiply everything by m1. And you'll see why I'm going to do that in just a second. It's going to really make things just a little bit easier for me. So if I go ahead and do that, I'll have m1 squared v0 squared is equal to m1 squared v1 final squared plus m1 m2 v2 final squared. And the reason I did this is because I know m1 v1 final is given by this equation right here. And now, right here, I have m1 v1 final quantity squared, right? I could rewrite this if I wanted to as m1 v1 final, all of that squared. So what I'm going to do is I'm going to take this equation I found up here from conservation of momentum, and I'm going to plug it in down here. So when I do that, I have m1 squared v initial squared is equal to, so this is m1 v initial minus m2 v2 final, that whole thing squared, plus m1 m2 v2 final squared. And now what I'm going to do is I'm going to go ahead and FOIL this out. And once I do that, I should be able to cancel things and simplify this expression. So here we have m1 squared v initial squared is equal to, so remember, when you FOIL, you take the first number and square it. So this is m1 squared v initial squared. And then we take plus the second number squared, so this will be plus m2 squared v2 final squared. And now we got to do 2 times the first number and the last number. So this will be minus 2 m1 m2 v initial v2 final. So here all I've done is I've just FOILed this. And then I have to add to this whole thing m1 m2 v2 final squared. And now we can see that there's a whole bunch of stuff that's going to cancel out. So on the left side, I have m1 squared v initial squared, and I also have that same thing on the right side, so we can cancel that out. So let me just go ahead and rewrite now with those two things canceled out. So that's going to be 0 is equal to m2 squared v2 final squared minus 2 m1 m2 v initial v2 final plus m1 m2 v2 final squared. Now the next thing I can do is notice everything has a v2 final in it. So I can divide the whole thing by v2 final. So it's going to get rid of this square here, it's going to get rid of the v2 final here, and it's going to get rid of the square here. Similarly, everything also has an m2, right? So we've got an m2 there, an m2 there, an m2 there. So I can divide off the m2, so that'll get rid of that square there, it'll get rid of that term, and it'll get rid of that term. So now if I rewrite everything, I have 0 times 0 is equal to m2 v2 final minus 2 m1 v initial plus m1 v2 final. So if I solve for v2 final, the way I do that is I move everything that has v2 final. So I take this and I take this and I'm going to move it to the other side of the equation. So I'm going to have minus m2 minus m1, all of this times v2 final, is equal to minus 2 m1 v initial. So these minus signs cancel. And if I divide off the m1 plus m2, I see that v2 final is equal to 2m1 divided by m1 plus m2 times v initial. So this is how we calculate the final velocity. So this is, if you give me any m1 and m2 and initial velocity, this is how you calculate that final velocity for mass 2. So now, if we go back to the equation that we found for mass 1, so this is m1 is equal to this equation right here. So let me write this down. We found that m1 v1 final is equal to, let's see, what was it? It's m1 v initial minus m2 v2 final. So if I plug this equation into here, I can solve for v1 final. So actually, let me just rearrange right now to solve for v1 final. So v1 final is going to be m1 v initial minus m2 v2 final divided by m1. So that's just v initial minus m2 over m1 times v2 final. So if I plug this expression for v2 final into here, I'll see that this is going to be equal to v initial minus m2 over m1 times, so let's see, we have 2 m1 divided by the sum of them, so m1 plus m2 times v initial. So we see the m1s cancel, so this is going to be v naught v naught minus 2 m2 divided by m1 plus m2, all of this times v naught. And then finally, if I want to just simplify things a little bit further, I can factor out the m naught, and this is going to be 1 minus 2 m2 divided by m1 plus m2. And then if I give this whole thing in here a common denominator, I can simplify things just a little bit further. So this is going to be m1 plus m2 divided by m1 plus m2. That's what 1 is. Minus 2 m2 divided by m1 plus m2. And when I do this, right, I've got an m2 minus 2m2. So that's going to be v initial is equal to m1. So m2 minus 2m2 is minus an m2. So we see that the final velocity of mass 1 is given by this expression right here. So it's the initial velocity times the difference between the two masses divided by the sums of the two masses. Now, it turns out that what we've just done here to solve for this perfectly elastic collision, even though it seems like what we just did is we solved this special example in which one of the masses was moving and the other one was at rest, it turns out that we can really use this method to solve any type of collision. And the reason we can use this method to solve any type of collision is that you can always change your reference frame to a reference frame in which one of the masses is at rest. So if you have two masses that are moving towards each other and they're about to collide and you want to figure out, what's going to happen, you just need to picture yourself in a reference frame that is moving along with one of those masses, so that one of those masses in your reference frame is initially at rest. Then you can use all of this that we've just found to figure out the initial and final velocities. So you'll have that the final velocity of mass 2 is 2m1 over the sum of the masses times the initial velocity, and you'll have that the final velocity of mass 1 is just equal to the initial velocity times the difference of the masses divided by the sums of the masses. So you can use this result for any type of collision as long as you put yourself into a reference frame where one of the masses is initially at rest.